Especially we have been concentrating on power graphs, something on commuting graphs, and this is another class of graphs from finite abelian groups. And of course, as I mentioned earlier, the very definition of Kelly graph was introduced by Arthur Kelly in 1876, and the very formal definition is this: you take a finite group gamma and its generating set omega. By a generating set, I mean to say every element of gamma can be product of elements of gamma, product of elements of omega, and this omega need to satisfy two conditions. One is C1 and C2. C1 is identity element should not be in omega, and C2 is nothing but every element in omega has got its inverse is also there. That's called a symmetric property, and it is because of the very practical demand in the case of parallel computing, in which Kelly networks are used as routing networks. And this Kelly graph is a graph construction from this pair gamma comma omega, for which the vertex set is gamma and edge set is x and y. They are vertices of gamma and they are joined provided y equal to x into A is an element of omega. If you recall the proof of Kelly's theorem, every element can be represented in terms of permutations. There the permutation image is defined in terms of this way: f a of x is xa or ax according to your choice of composition. And whenever this is being referred, the credit goes to Kelly because of that representation. And the Kelly graph is denoted by Kelly of gamma comma omega. And that was with regard to finite groups. And in 2005, Focus defined Kelly graphs of rings. Suppose R is a commutative ring and C is a subset of R with the property that C is equal to minus C. That's what I said in the case of groups C2, every element has got inverse in omega. Similarly, here for every element A in C, minus A is also there. That is a symmetric property with respect to addition. And with such a subset, the Kelly graph of a ring R with respect to C is constructed. It is nothing but the vertex set is R, edge set is x and y. They are distinct. They are joined by an edge provided x minus y is in C. The difference of x and y is in C, and literally it is nothing but y is equal to x plus C, something like that. The same y is equal to xa. So this was introduced by in 2005 and it is studied. Of course, a very simple example of a Kelly graph, either you can treat it as a ring or a group. If you take congruent modulo 5 classes with respect to addition modulo 5, and the omega is nothing but 1 comma 4, 0 is not there, the inverse of 1 is 4 and vice versa, and this is the Kelly graph constructed out of this one. Of course, you can look at here, it is regular, and the degree of the regularity is nothing but the order of the generating set. Okay, and this is another example in which the vertices are congruent modulo 9 classes, and the vertex set is, the generating or the subset is 3 comma 6, and you can see this graph. And just I would like to get opinion from the audience that are there any difference between these two Kelly graphs? The first one, congruent modulo 5 classes and 1 comma 4, and the second one, congruent modulo 9 classes with respect to 3 comma 6. Could you observe any difference? Somebody was saying that it is not connected. So previously this graph is connected, this one is not connected. Of course, it has been proved that it is quite natural to see that Kelly graph is connected if and only if the underlying group is generated by the omega. Here 3 comma 6 is not a generating set because either of them is not relatively prime to 9, hence it is not a generating set, this is not connected. However, it is regular, the other things are okay. And in 2010, Ashraf et al. Communications and Algebra, and they defined another graph called Cayley sum graph. Just you can see the adjacency relation in this case, here x minus y is in C. It is a difference. Just you make this as x plus y. That is what Cayley sum graph. Let R be a commutative ring. Again C is a subset of R. Then the Cayley sum graph, here there is a plus that denotes the sum R comma C, which is a graph with vertex set R and edge set is, as I said, x and y are joined provided they are distinct, and x plus y is in C, then this is Cayley sum graph. And with the knowledge of something on the bijection, because every element has got a unique inverse, even I was under the presumption that the Cayley graph and Cayley sum graph might be the same, or there must be some isomorphism, because x minus y is uniquely related to x plus y, but it is not so. The very first reason is you take Z5, take 1 comma 2, then this is the Cayley sum graph with respect to this 1 comma 2, and this is not regular, thereby they are not isomorphic, and ultimately the study on Cayley graphs and Cayley sum graphs need to be attended differently. Of course, for the sake of audience, I tell you there are only 3 papers appeared in Cayley sum graph as of now. There are no much work is done. It is only the basic work and 2 more papers. So that too, one is on ideals, the generalization to ideals of R. So anybody would like to have any interest, you can explore the possibility of the Cayley sum graph. Okay. Now naturally the generalization takes place. Some generalizations I would like to put forth. Sengupta et al. In 2015 introduced a graph called square element graph of a commutative ring with identity. And the very definition of square element graph of a commutative ring R is nothing but SQ of R, the vertex set is non-zero elements, just 0 is being deleted, and 2 distinct vertices are adjacent provided A plus B is x square for some non-zero x in R star. So because of this property it is called the square element graph, and subsequently the same set of others they have extended this definition to arbitrary rings. The initial paper they considered commutative ring with identity. In the 17th paper they consider R need not be commutative with the same definition. And Snowden in 1982, much earlier than this, he studied the same concept for the transformation group of semigroups. In fact, there are parallel constructions on groups, rings, similarly on semigroups. Okay. So what we would like to have it is, why don't we explore the possibility of having the square graph or square element graph for finite abelian groups. And we started this, let G be a finite abelian group, and the square element graph of G is denoted by gamma SQ of G, for which the vertex set is G, and 2 distinct elements are adjacent provided x plus y is equal to 2t, because when I take a finite abelian group, naturally people used to take it as addition, because abelian operation is always written as addition. Therefore t square becomes 2t for some non-zero t in G, and 0 is the identity element of G. So this is the definition of square element graph. And having introduced, we would like to explore what are the parameters or how best you can do the structure of this square element graph of finite abelian groups. Of course, the very fundamental tool is from algebra, the very structure theorem for any finite abelian group. Any finite abelian group can be written as direct product of finite cyclic P groups. So if G is a finite abelian group of order P1 to the power alpha 1 etc. P K or PR to the power alpha r, where Pi's are distinct primes and alpha i's are distinct exponents of the corresponding Pi's. Then G is isomorphic to direct product of cyclic P groups ZPI to the power alpha I. And this is being used as a tool for this entire observations. And of course, not only that, there is a concept of partition of an element, partition of an integer, and partition of a positive integer k is nothing but writing k as the sum of positive integers between 1 and r, 1 and k. So this plays a role in the discussion on square element graph of G. And of course, we used to write the partition of alpha I as alpha I1 etc. alpha I ik is the number of positive integers in that partition, and this is being done. And for the purpose of finding the structure for a given finite abelian group G, let me take G1 as a set of all 2t for different elements in G. So for every element G in T in G, we take 2t, and the complement is being taken as G2. And ultimately, this is the tool for the proof of any property in that graph for any k tuple A1, A2, AK, and this XL is being defined by this way, and this HI is nothing but Z2 to the power Ni G1. G1 is here and the complement is G2. So with this notation, we take the direct product as this one. These XLs for L is equal to 1 to something R up to R, they play vital role. Of course, when I take G is divisible by 2, then the prime number P1 is 2. I take this as a direct product of this is the partitioned component of the direct product. Actually, this is suppose this P1 is 2, alpha 1 is there, this is 2Z2 to the power alpha 1, that is being in turn partitioned with respect to partition of alpha 1, and all the remaining components are being taken as sketch, and this, so this is the only tool. Just how do we manage, I would like to put forth, that's all. And these are the properties we could observe. The degree of the square element graph is being determined. And of course, you can note that it is biregular. Either the degree is cardinality of G minus 1, order of G minus 1 or order of G minus 2 according to the nature of the elements, whether x is 2x equal to 0 or not. Then it is connected. Diameter is 2. Of course, I am surprised, maybe I don't know the reason for that. Almost every graph, except 1 or 2, almost every graph constructed from algebraic structures, either it is a ring or a group or semi-group or vector spaces even, the diameter is less than or equal to 3. It is the, what is the reason, I don't know. When I referred this to Professor Katona, he was replying that there is a probabilistic proof for almost all graphs are of diameter 3. So what we deal with the tree and all that, they are only negligence class. He was saying that there is a probabilistic proof, probability of a graph having diameter 3 is almost 1. So he says your class is a major class, but as a graph theorist, we always draw path first and then some cycle, something like that we are doing. And for this class, it is diameter 2. Of course, either 2 or 3, it is 2. Then grit is a similar observation in the case of grit. Grit is either infinity, in which case the graph does not contain any cycle. If it contains a cycle, it is 3. Okay, and this is the refinement of a star graph, K1, cardinal order of G minus 1. Refinement, we see, we divide the edges of this star graph. And we could prove a structure theorem. Ultimately, we have proved that the square element graph of G is nothing but disjoint union of 2 power k induced subgraphs induced by this is the induced subgraph XL. In the previous slide I have defined what is XL. It is a particular case of a particular type of direct product as per the group structure, and as a graph it is a disjoint union of this one. And of course this G1 is spanned by X1 and G2 is the union of the remaining. And we have divided the further properties into two cases. One is order of G is even, another one is order of G is odd. When order of G is even, naturally the order is divisible by 2. In that case, let me take order of G as 2 to the power alpha into T. T must be relatively prime to 2. Then let me take the partition of alpha, that is equal to sigma I is equal to 1 to k alpha I, which is equal to alpha. Then this is the entire thing is depend upon this k. This number of partitions in the of course the formula for partition is a very difficult problem. As of now, the partition, a better asymptotic formula is by Ramanujan using nth primitive roots of unity. And as far as this number k, the entire thing stands on, the degree is varying, and you can see the difference. It is 2 to the power k here. And either it is a complete graph, the graph induced by x1, either it is complete or refinement of this one. And further we could observe what is the structure of this XL using how long this number is 1, this alpha is 1, because P1 to the power alpha n etc. PR to the power alpha r. Suppose P2 to the power alpha 2 is 1, then as per this condition we collect the exponents which are 1. So up to starting from 1 up to m, if it is 1, then this thing. So it is partially 2 power m refinement of star graph, and the remaining are regular graphs. And diameter is infinity, width is either 3 or infinity, fine. And naturally we would like to explore what are the other parameters for this graph. Independence number is determined. Independence number is a set with maximum cardinality in which no pair of vertices are adjacent, and that we could do it the independent number according to the order again. If order of G is even, then depend upon this the independent number. Of course people with very good knowledge in graph theory, independence number is denoted by alpha. Why you are using beta? Because alpha is our exponent, we cannot combine that, we are forced to use the different number. So the independence number is either 2 or either 2 power k or 3 into 2 power k minus 1 or 2 power k minus 1 or 2 power k plus 1. And the click number also we could determine, and of course which is depending upon all the other things are the previous assumptions. Let me take T as set of all x and g such that x equal to minus x, that is the set of all involutions in G. An element which is having order 2 in an algebraic structure is called involution. So this is set of all involutions, and they are the square of some element in G. And let me take this as T, and this T plays a vital role, and as per the cardinality of this T, the click number is either cardinality of T or cardinality of T plus order of G by 2 power k minus order of T by 2. Okay. And the chromatic number, and please see the only no difference at all, just you can look at here the same thing here. Of course the chromatic number is, you should have proper color, the least number k in which the graph is k colorable. And with this same assumption we could prove that the chromatic number is of this one. And if the chromatic number is equal to the click number, the well known weakly perfectness, and of course it is also my observation that almost all the graphs constructed from algebraic structures weakly perfect. So why I put forth this is we are unable to find or characterize an algebraic thing which makes these things possible, because there are a very different scenario in either in the ring or in the group or in the vector space, but when we construct the graph it becomes weakly perfect. Maybe my observation is one thing is, all these constructions, they are not taking the entire algebraic structure into consideration. It is only the partial consideration. Maybe the complicated part is not getting into the graph theoretical part. Ultimately this happens, I feel so. So this square element graph is weakly perfect and it is not Eulerian, and this is pancyclic. For every index k in between 3 and order of number of vertices in that graph, there is a cycle of that length, and it is proved that this graph is vertex pancyclic, because there are two versions, one is vertex, another one is edge version. And of course, having done something on square element graph, why don't we consider this complement? Of course, up to the previous part it appeared in AKC, and this complement, this has appeared in Houston Journal of Mathematics, and we could do the structure of the complement, and it is connected if and only if order of G is even, and the same thing, diameter is known, and please note that either it is complete or the diameter is 2, girth is either infinity or 3, independence number, it depends upon, you please see the right hand side cases, it entirely depend on the direct product and the group structure. As I said, there is a fundamental theorem which gives you the entire direct product of any finite abelian group, and depends upon the components of the direct product, this independent number gets varied. And again this is also weakly perfect. So once you become this and the graph is weakly perfect, you can see that the perfectness, it is not Eulerian, this is vertex pancyclic. Okay. So this is one part of the problem. So naturally one would like to have what is a further generalization. We have been discussing for a p is equal to 2. Now that I would like to explore the possibility of p equal to 3. Just my difference is, instead of 2t, what will be the case if it is 3t? And naturally we have done everything in parallel, the same scenario, you can see cubic graph means, for the sake of recall, the same vertex set, only difference is x plus y is equal to 3t for some t in G, this one. Similarly, I am taking G1, G2, the other, the same scenario, almost the proof technique is very similar, nothing is very difficult. We can parallelly work it out and find it that degree of this vertex connected, diameter, girth. So in the general case also, when I take in the case of square element graph, whether it is even or odd, or whether it is divisible by 2 or not. Here my consideration is whether the order is divisible by 3 or not, and parallelly things are being worked out. Okay. So independence number, it is weakly perfect. When it is not divisible by 3, it is vertex pancyclic and not Eulerian. And as I said, there we have our properties. The square element graph is connected if and only if order of G is even, that is divisible by 2. The same thing here, order of G is divisible by 3, the complement is connected. And this is weakly perfect. And please note that in the previous case it is never Eulerian, but here are the situations. This complement of this G is Eulerian if and only if G is isomorphic to Z3K, it is Z3 times K, or Z3 to the power K times Z2 to the power R. So the cubic graph, complement of the cubic graph is Eulerian if and only if in the direct product of the finite abelian group, the components are either Z3 or Z3 and Z2. So that is the case, and it is vertex pancyclic. It is perfect because it is weakly perfect, both the graphs are weakly perfect. Okay. And naturally, what could be the next generalization? Any audience? So I discussed with 2 and then I discussed with 3. Natural thing is go for 4 or something else. So it is not 4, it is for some prime P. So this is the work combined with Peter Cameron. The previous work, myself and my students Ravindra Pratap. This, when we would like to explore for any prime P, then it was combined with Peter Cameron. It appeared in Graphs and Combinatorics. And of course, the very generalized definition is instead of considering x plus y is equal to 2t or x plus y is equal to 3t, just we take finite abelian group G and one of its subgroup H. Okay. The definition of subgroup sum graph, which is denoted by gamma G comma H. So a finite abelian group G and a subgroup H. Corresponding to that pair, we define gamma G H. Okay. The vertices are elements of G and 2 distinct elements are joined provided x plus y is an element of H, but it is not 0. Okay. Then why you are deleting 0? Cameron wanted to say that no, we can have this as extended subgroup sum graph. So when we delete the condition that x plus y is non-zero and an element of H, just you say you take the same graph, same vertex set, only difference is x plus y may be 0. Only condition is x plus y is an element of H. So this is the definition of subgroup sum graph. So we take a subgroup, we demand x plus y is an element of that subgroup. And naturally, for this subgroup sum graph, this either the square element graph or the cubic graph or subgroups are particular cases of this one, because any prime power of elements and its prime power form a subgroup in G. If we take P is equal to 2, all squares of elements form a subgroup. Similarly, the case of 3, in general, if you take a prime number, all prime multiples form a subgroup. Therefore, this previous graphs are subgroups of this generalization. Okay. And when you take H is equal to 0, the subgroup sum graph is nothing but null graph, because you demand x plus y is non-zero and 0 is the only element. Therefore, there is no possibility of any edge in G. Okay. And the extended subgroup sum graph is a partial matching where the elements other than the identity and the involutions are joined to their inverses. Structurally, what is the difference between subgroup sum graph and the extended subgroup sum graph? Just the extended subgroup graph can be obtained from subgroup sum graph by adding this all the elements to the identity element, because x plus 0 is equal to x, and all the elements which are involutions, x plus x equal to 0, that is x equal to minus x. Therefore, this is the extension of this. And what are the structure of subgroup sum graph? And literally, the entire fact stands on the very convenient algebraic structure, namely cosines. When you take a finite abelian group, every subgroup is normal. So naturally, you can have the quotient group, or even you don't have a normality of the subgroup, you can consider all cosets of a subgroup in a group. So you take all cosets, let the order of the subgroup be K and order of the quotient group be M. There are M cosets in M cosets of H in G, and according to the order of the cosets in G by H in the quotient group, the entire structure is defined this way. The extended subgroup sum graph gamma plus of G comma H has M plus S of G by H. This S denotes, you please see here, this S is nothing but cosets of having order 1 or 2 in G by H. So the entire structure depends on G by H, cosets and their orders. This S of G by H means this is set of all cosets of having order 1 or 2. So with that in mind, this is nothing but M plus S of G by H by 2 connected components, out of which S of G by H are complete graphs KK. This K, you know the order of the subgroup, and the remaining M minus S of G by H by 2 are complete bipartite graphs KKK. Then this one. Of course, I am reminded of the fact that there is a notion called total graph of a commutative ring. You take a commutative ring R, you take the non-zero elements of R as the vertices, and two vertices are joined provided their sum is a zero divisor in R. That is having the same structure. Here, literally speaking, it is the union of complete graphs and complete bipartite graphs. That is the same case in the case of the total graphs of commutative rings, and we could extensively study about the total graphs. The graph was introduced by Anusandhan and Badavi, the co-authors of the book, but we explored in a greater dimension about the total graphs. So I am reminded of the fact here. Then about the subgroup sum graph, the same notation, order of H is K and order of G by H is M. Then the subgroup sum graph gamma G by H is obtained from the extended subgroup sum graph by deleting a perfect matching from every component which is complete bipartite and deleting a matching from a complete component of a coset H plus A covering all elements other than the elements of S of G lying in this coset. So it is a reversal process. What we do, we know the structure of the extended subgroup sum graph. This extended subgroup sum graph, the entire structure is known. It is the union of complete graphs and complete bipartite graphs. So what we do, from the complete bipartite component, you delete a perfect matching. From the complete component, you delete a set of vertices. Then you will get the subgroup sum graph. The subgroup sum graph is obtained from the extended subgroup sum graph by deleting a perfect matching from the components of complete bipartite graph and deleting a matching from complete subcomponents. So that gives you, and ultimately this equivalence is being determined. Let G be a finite abelian group and let H be a subgroup of G. Suppose cardinality of G is order of G is greater than 2, then the following are equivalent. The extended subgroup sum is connected, subgroup sum is connected, H is equal to G. That is why it is put up under this is H is equal to G. So what it means to say, the subgroup sum graph is connected only when G equal to H, otherwise it is disconnected. That means to say that the number of components either complete or complete bipartite is greater than or equal to 2 in when you take H as a non-trivial subgroup of G. Okay. And because we have observed that both the cases of square element graph and cubic graph, the graph is perfect. So naturally the interest is what about in the case of this one. the subgroup sum graph and extended subgroup graphs are perfect graphs. And of course, this is purely a part done by Cameron, and the paper was sent to graphs and combinatorics. The referee could not understand the proof of that particular theorem. He returned back, and we were a little bit worried about, because we are convinced about the proof. When we communicate with the Cameron says, what is the problem with the referee? Why he doesn't understand? Okay, let us leave it, and he has written in a other way. Then only the referee could accept that. Even the referee appreciates, but however he could not follow the argument. So just we remember that quite. So it is purely by way of argument, not in the previous cases. The proof was a little bit elaborative in the cases of square element graph and cubic graph. Here the argument was something different through some labelings of the vertices and the other properties, some arrangement of these vertices in some order. Okay. So as this is a corollary, our results are corollary to this one, and as done in the other cases, because this structure is trivially known, the clique number and domination numbers are studied, and spectral properties are observed. Then, okay. So one more generalization which was suggested by Cameron, and still it is not explored. So x plus y is equal to 2t one case, x plus y is equal to 3t another case, x plus y is an element of non-zero element of a subgroup. Now we go for one more addition with respect to two subgroups of G. Let H and K be subgroups of the abelian group G with condition that H and K are different. Then we define the generalized subgroup sum graph gamma G H comma K, which is a graph with the vertex set G and two distinct vertices are adjacent provided x plus y in H. One more condition, x plus y is not an element of K. So we demand it is an element of the subgroup, but it should not be in the choice of the other. So I wanted to be in H but not in K. And this definition as of now is not explored. Just it is given in the open problem in the graphs and combinatorics paper. One of the student is trying something, but we have not progressed much about it. Still it is open. And these are the references. Of course, the other things I didn't list out just for the sake of this one. So I think I can stop at this stage. Okay.
We have time for questions, remarks, so please, yeah.
Thank you, sir, for insightful presentation. I just want to ask whether there is any work carried out towards the spectral approach, spectral theory approach.
Yeah, almost for the subgroup sum graph, the spectrum is given.
Okay.
The entire spectrum is known
Okay.
because of the structure of the graph.
Okay. And which classes of these graphs are more symmetric in the sense vertex transitive like that? For the spectrum purposes, we need graphs which have more symmetry.
You mean vertex symmetry?
Yeah. So is there any class which is more symmetric so that we can work on this class?
I don't have any observation in this regard. Someone has to look into that.
Okay, sir.
So as of now, I don't have any idea about it.
Okay, thank you, sir. Nice presentation.
Sir, good morning.
Good morning.
Thank you for your nice presentation. I have two doubts. Why we have defined x plus y equal to 2t? That is the first thing. And another one is for this sum square sum graph something. The domination parameters were studied on these graphs because your survey is already exist on domination.
Yeah, that is, no.
That is for Kelly graphs.
Yeah,
only,
yeah,
sir. Yes,
these
sir.
were Kelly graphs.
Whether-
AKC paper you are referring.
Yes, sir.
Okay, that is a
Whether-
survey on Kelly graphs.
Whether the domination is fine for these graphs.
One thing is, this class doesn't come anything, because that type of thinking still we didn't put forth. Whether this class and Kelly graphs have got any intersection, I don't know anything about that, number one. Number two, here this is KK, you didn't KKK. The domination is immediately known. Just because you can pick up the convenient vertices from the components and ultimately it's known. So it's not a very complicated issue. So trivially it is, or very easily it could be done.
Okay, sir.
But in the case of Kelly, the problem is still more complicated. In fact, when we started the work on Kelly graph, we presumed that the things could be settled in an easy way. When I discussed in one of the meetings with Sandy Classer, because he had a big work on binary cubes, he said the problem is complicated. Still in the case of Kelly graphs, the domination is open, but it is with respect to the generating set. The property of the generating set plays a vital role, so because of that, that is there. And we could do something on circulant concretely, that too depend upon again the nature of the nature of the generating set we are taking. That's the status of the problem.
Thank you, sir. Sir, what about x plus y equal to 2t, sir?
And naturally, I said that the Sen, he has introduced that, I think Sen only introduced the square element graph.
Okay.
X plus y is equal to t square.
Yes, sir. Yes.
That is with respect to multiplication in the ring.
Okay, sir. Here
When we were come for the group,
addition. Yes.
addition only there.
That's right.
And naturally, that's what I said. In the case of abelian group, people used to write plus.
Yes.
Because of the abelian behaves like plus in integers, so it is written as. So t square naturally 2t.
Yes.
It is t plus t.
Yes, sir. Understood.
So similar in the case of this one.
Understood, sir. Thank you, sir.
Sir, my question is, for the case of square graph, if 2 is a generator, then all the elements is a multiple of 2, then the graph may be
2 is a generator of G, you mean to say.
yes.
What do you mean by 2 in that case?
The group
Suppose
is,
G is a abelian group,
no sir, I am talking about Zn. If
Zn,
n is
Zn,
a-
okay, fine.
n is an odd number, then 2 is a generator of,
No, you are talking about Zn
yes,
with respect to addition modulo n.
yes.
So you are taking 1 plus 1. Sorry, 2, you are taking 2, okay. What do you say?
N is odd, then 2 is
You
a
take n is odd and 2 is a generator of Zn.
then every element is a multiple of 2.
Yeah, definitely.
So the graph is complete.
Graph is?
Complete square sum graph.
No. You see, you are, when you are saying I am taking 2t, it is t plus t. Your 2 is different from here, t plus t, not that, your concern is, don't confuse this number 2 and this t plus t.
It's okay. It's clear. Sir.
Yeah,
it's
don't
clear.
confuse that. It is always that, even in the paper of Anderson and Livingston, the zero divisor graph, R is a ring with identity, 2 is nothing but identity plus identity, not the number 2. People always under the impression that it is integer 2. It is not integer 2.
It's okay, sir.
Am I
Thank you.
correct? Okay, fine. Thank you.
Sir, in the open problem that you had mentioned, you mentioned about H and K. Are there any restrictions imposed on H and K in such a way that K is a
When the
subgroup
problem
of
is
H?
suggested, just only condition is x plus y in H, x plus y not in K.
So if we are considering K to be a subgroup of H of the something of that sort, then immediately
No. In the definition.
No, you didn't mention that, but then it would be an immediate generalization.
Please, just a minute. Already K is a subgroup of G.
Yes.
Okay, then any other restriction you wanted to impose, you can put forth.
Okay. So even
This
if it's
class can be studied by adding some more conditions on H and K as per your convenience. What you need, you have to decide on the problem which you are taking. Just like that, I cannot say this you can put forth. Or the other way, when you assume something, you must be able to progress your path. Maybe you can put forth.
Okay, sir. Thank you.
Okay, fine.
Okay, so let's thank the speaker again.
Thank you. Thank you for the.
Thank you, Professor Alexander Wessel, for chairing the session. I request you to honor the speaker and Professor Tamil Selvam T to accept our token of gratitude. Thank you, Professor Alexander and Professor Tamil Selvam T.
As we conclude the first two sessions of the day, it is time for a well-deserved break. We invite you to join us for a refreshing morning tea break. I request everyone to be back by 11:25 a.m. I request everyone to be back by 11:25 a.m.
Verghese, and the topic is From Brain Anatomy to Network Topology. The chair for this session will be Professor Aparna Lakshmanan S., Department of Max, CUSAD. I invite you, ma'am, to chair the session.
Good morning to all of you. As they have already mentioned, the next speaker for the session is Dr. Seema Verghese. In fact, they have given a short essay about Seema Verghese to me to introduce her to all of you, but I am not going to read all the content in this. You can just check the website to find all these details. I want to make it more personal. I would like to call her as Seema Chechi rather than Dr. Seema Verghese. Actually, she is my academic sister in the sense that she completed her PhD from Cochin University of Science and Technology under the guidance of Professor Ambad Vijay Kumar, who is also my guide. So we are academic sisters. Even before that, in fact, she is my teacher. While I was a student at Cochin University doing my master's in mathematics, she only taught me graph theory for the first time. So I learned graph theory from her. So I'm very happy that I'm given the chance to chair her session. With this brief introduction, I invite her to talk about From Brain Anatomy to Network Topology, or totally, yes? Okay, so the thanks goes to Francis Raj. In fact, he was supposed to chair the session. When he saw me, he just told the organizers that it will be better that I introduce her because we are personally connected. So thanks to Francis Raj for the opportunity. And you can see that the topic is totally different from what you have heard during yesterday and today morning. This is something, an applied side of graph theory. I believe that this will be of interest to all of you. With that, I welcome Seema Chechi for the talk.
First of all, let me congratulate Christ College, the management, department, faculty, Department of Mathematics for organizing such an event. I think it has become a habit for them to organize conferences every year, and it is very beneficial to our community. And today, this day is very special for me. It was on 2001, September 19th, I joined for research under the guidance of Vijay Kumar sir. So this is the 25th year. I still remember the day which I joined. I went to the office there. I completed all the procedures. I went to Vijay Kumar sir, and we talked for some time. Then I went to the research room and occupied my seat. Still, all that thing is very fresh in my mind. You may be wondering why I am talking about these things now. There is a connection with my topic. Because on September 19th, whatever I have done during that process, I remember it very clearly. But what I did on September 20th or 21st, I don't remember. Okay, why is that? So you are going to get an answer or a partial answer while going through this topic. Now, all of you had your tea, snacks, everything. Why do you eat, or why do you have your breakfast? Why do you see when you are having your breakfast? Say you may be eating 1 idli, 2 idli, or something like that. You first of all, your brain will tell you. So you have to have your breakfast. So you will have your first idli, second idli, third idli. Then maybe brain will tell you, say enough. You are on diet. See, everything is controlled by brain. Okay, and you may be. It's a curious. It was very curious. I was very curious about how this happens. Okay, for that we need a little bit of biology. And why we are going to learn that biology? It's because there is a very emerging topic, area where graph theory is very rigorously used in brain networks or neuroscience. Okay, so for that, to understand how it is used, we have to learn, or we have to understand the story of the nervous system. What is the story of nervous system? See, is it is one fine day the nervous system originated? No, it was not like that. The nervous system evolved from a single cell organism. In prokaryotes, that means prokaryotes means single cell organisms, it had the ability to respond to the circumstances. It had the ability to respond to the circumstances. And with that ability, it did, you could say, if you remember, you are in your high school classes, you maybe thought about how amoeba catches its prey. Okay, so whenever detects some amoeba detects some prey is there, it will bring forth its pseudopodia and engulf it and take its prey. So that is a response that is done by the response system. That response system, from the single cellular organisms, when it involved into multicellular organisms, and when it was speciated, or more and more species came into picture, this nervous system also developed. And it will be of interesting to note that what's the difference between human beings and other animals? What is that? What is the main difference? It is the ability to think, to process, to understand. That is the cognitive ability. Now how that developed, it's very interesting story. It's because of some new mutation. The primitive man, or the species which were our predecessors, they were called Neanderthals, and some mutation happened to these Neanderthals, and due to that mutation, what happened is that the frontal part of the brain, it started developing, it started producing more and more cells, and that matter, that brain matter, frontal matter developed. And it is that difference in the center in that frontal lobe, that we are Homo sapiens and animals not. So we can think, we can organize, we can process things, or everything because of the frontal lobe of that. Now also another example is that you may have seen singers. So see, some are very good singers, some are professional singers, then there are bathroom singers, and there are some other people who like music but may not be able to sing. So what's the difference between them? So the difference is that, first difference is that the area which respond to hearing, the hearing area, the neurons in that area is well developed. They can hear it, they can make out the differences between the single notes, and they can reproduce it. So that's why, so each and every capability we have, it depends on the nervous system, which was evolved from the prokaryotes to the human beings now. So this, our nervous system, it is a complex one. It has two parts. It is called, the first one is the central nervous system. It consists of the brain and the spinal cord, and the peripheral nervous system, which are the nerves which will communicate from the central nervous system to others, and in and out of the central nervous system. You have the peripheral nervous system. Now this is the story of that evolution. You can see in different organisms, there are the network of neurons. See, in the first one, it's just a net. There is nothing over that. And you can see when it comes to here, lizard and all, there is a development like it has a brain. Here also it has a brain. So, and all other central nervous systems are there. So now this is the part of evolution. So after part of in human beings we have the most complex nervous system consisting of the brain and the peripheral nervous system. So this is the anatomy of the brain. You should know why we are talking about this anatomy. See, brain is for our convenience, now it is divided into to learn or to study, conduct experiments, it is divided into lobes, different types of lobes, and this is the frontal lobe which I told you, and this is a parietal lobe, occipital lobe, all those things, and each and every lobe has each specialized functions for that. Okay. Now coming to the microscopic structure, that was anatomy. What about the microscopic structure? This person is of very importance, that is Santiago Ramón Cajal. He was the first person to begin a serious clinical investigation to the structure of the brain. He is credited with the discovery of neuron, and neuronal theory is the foundation of neuroscience. What is a neuron? A neuron is a nerve cell, and so before that you must understand, when I say nervous system, what do you mean by a system? That is also important. See, our body is made up of cells and specialized. Some cells are very much specialized, and specialized cells form tissues. Then tissues join together to form organs, and organs join together to form systems. So there are many other systems also. You have digestive system, you have reproductive system, you have excretory system, respiratory system, all those things. Like that, one system is nervous system. Okay, so in nervous system, what are the organs, or this is the brain and the spinal cord and the other nerves. Now each and every nerve or each of these organs is made up of tissues and cells. The basic building block is cells. So how does the cell of a brain look like? So each cell, for each organ, the cell is different. The constitution of the cell is different. For a brain, the basic cell is called a neuron. So neuron is a nerve cell which communicates with other nerve cells through electrochemical impulses and transmitted via synapses. Synapses means just connections. It is the ability of the neurons to grow and multiply and to create connections between other neurons. That is the process of learning. So whenever neurons are multiplied and whenever neurons establish connections with other neurons, you say that our brain is developed. See, this type of development is happening, the dynamics is happening in two ways. First one is the dynamics in the brain happening from the childhood to the adult. So when you know that when a newborn baby it's not able to speak or able to do whatever functions which we do. Okay, why? Because the neurons are not that developed. Now in the process of the growth, he attains more and more neurons, and the brain become developed, and he is able to do the activities. So that is one type of dynamics happening in the brain. Secondly, there is a dynamics which is happening through the evolution, that is throughout the generations. That dynamics may not be visible to us because we are in just one point of that evolution. So it happens in generations only. One type of evolution is that what I told you earlier, the mutations happening to the frontal lobe. Okay. So these are the two types of dynamics, and this is the basis of neuroscience, and he was awarded Nobel Prize in 1906, and this is the person, and this is the structure of a neuron. So this neuron consists of a first thing called a cell body. Here there are some other organelles called what are the things inside the cell? They are called organelles or cell organelles. So you have the nucleus, endoplasmic reticulum, mitochondria, all those things. So each of the organelles have its own duties, and it has a tail-like structure called axon, and this here you have the dendrites, and this dendrites is attached to the cell body of the next neuron. So can you see a graph structure here? Yes. This is the point where neuroscience meet graph theory. And there is one idea which was put forward by the student of Ramani Kayal, that is Donald Hebbs. The statement was that neurons that fire together, wire together. That is the answer to my question. Neurons that fire together, wire together. What was the question which I asked you in the beginning? I remember whatever happened on September 19th, 2001, but I don't remember what has happened on September 19th September 20th. I don't remember. Why? Because September 19th was a day of emotions for me. I had so many expectations. I was very happy to do that. So it was full with emotions, and the area which is controlling emotions, that area is called amygdala, and it is very near to the area which creates memory and stores memory, that is hippocampus. Okay, so this area, emotions and memory, the area is very near to the, physically they are near together, so that whenever you are emotional or when you have emotional events, it is remembered. Okay, that is the answer. Now, this is the idea, and you see this is what happens when you speak, or this when you speak what you said. When you are answering a question, first of all your ear will process, and it is something happening here, then it will be comprehended, then it will be formulated, the response will be formulated. This is what is happening. So each and every region have specific functions, and they coordinate together to form to get the result. So each functions which coordinate together, they should be connected. So how well it is connected, it is the idea, how well it is connected. Now, so what is the idea is to look at the connections of neurons using graph. So, we saw that neurons are, you have the cell body and the tail is connected to the next cell body. So it's very good idea to take one vertex for each neuron, and the edge, the connection will be established if there is the edge will be established if there is a connection. But the problem is that there are 100 billions of neurons. The number is so large that we cannot take such a big thing to do and work with that. So what is the idea? Instead of taking one vertex for each neuron, we try to define vertex as each area. So each area we have divided into some areas, and each area you will have a vertex, and if there is a connection between the areas, you will have the edges also. And remember, it's slightly different from the normal graph or simple graph. Here the areas are of different capacity. So in the brain network you should have vertices of different size. The edges, the strength of the edges is also different. The strength of connection is also different. So the strength of the edges is also different. So you are going to get a weighted, and also it is directed. So weighted directed graph as the model of brain. Now whenever you have a graph, you have the adjacency matrix, and this adjacency matrix it is called the connectivity matrix in neuroscience. Why? Because brain has three types of connectivity. The neurons are connected. There are three types of connectivity going there. That is, so this is the structural network. This is a symbolic structure, not the exact one. So here you can see vertices of different sizes, and colors are also that is also important for some type of identification, and the edges are also weighted. The weights will be attached to the edges when you form the matrix. So this matrix is called adjacency matrix of the brain is called the connectome. It is the central idea about brain networks. It was first coined in 2005. It was in 2005 that neuroscience first used graph theory as a tool. It is the state of knowledge of the cellular wiring diagram of brain. the matrix representing all possible pairwise anatomical connections between neural elements and the brain. Matrix of there has been tremendous development in this area because of two factors. First one is the rapid growth of network science, that is graph theory. We have a rigorous theory, we have so many tools, we have so many graph metrics, so many things which is happening. With graph theory has very tremendously developed throughout these days. And the other part, there is a technological evolution which to measure and visualize the brain organization. That is, we want to get some signals from the brain, and for that some technology was developed. So many technologies for example fMRI, it is a functional magnetic resonance imaging, EEG, these terms you may have heard if you have consulted a neurologist or something like that. So on account of these two factors, there is a very good development in this area. The first fully constructed connectome belongs to the roundworm. This efforts to build the connectome, it's not that easy. The first one was done in C. elegans. C. elegans means the roundworm. This is the roundworm, and this is the connectome of roundworm. And you can see very simple organism. It has such a complicated structure. It has around 300 to between 300 and 400 vertices, and around 7, 8 or something 800, not 800, more than that. So this itself is not easy to analyze. Then there is another organism called a fruit fly or Drosophila. It was the full connectome was developed in March 2023. It consists of 3016 neurons and so many around 5 lakh synapses. This is the Drosophila connectome. Now research is going on connectome of monkey, rhesus monkey, and so many positive results are there in connective. Now what about the human connectome project? It is a project to map all the neurons and their connections. It's not finalized, it's still going on. It is sponsored by National Institute of Health, United States. Now why you can use graph theory here is because graphs are simple models that anyone can understand. Even neurologists or biotechnologists or those people who don't have any rigorous training in our area, they also can understand graph theory. So that is one important advantage of graph theory. And how will you use this? Or where is the, what is the idea? We can use this to diagnose and predict the diseases which is happening to brain. For example, if you are looking at Alzheimer's disease or Down syndrome, most of the research is done on Alzheimer's disease. Why? Because it is a very progressive disorder, and if it is diagnosed early, at early stage, it is manageable. And that in that diagnosis, this graph theory or the metrics of graph theory, graph metrics will be very useful. I will just talk about that later. And remember, when you model brain using graphs, there are some limitations. That is, the dynamics is not taken care of in our simple graphs. So if you want to include that also, you should think of some what is that, stochastic procedure or something like that. It should be applied to graphs and then work on that. So here as a beginning stage, it is not done like that, but still this part, the symbol graph, is also very useful in the neuroscience. I told you there are 3 types of connectivity in brain. First one is the structural connectivity. Structural connectivity means whenever the areas are near, the functions coordinated by them will be simultaneous, or it happens very near. That is the structural connectivity, but we are more concerned with functional connectivity. What do you mean by functional connectivity? In functional connectivity, the areas are not physically near, but the functions they correlate functions done is correlated. There is a correlation between them. See, you can think of some functions which is done simultaneously. For example, the first example was that memory and emotions and memory, their areas are near and they are done simultaneously. That is one example. Second one, there are some other functions which are coordinated by different parts of the brain. That is, if you are making a speech and you are walking, so making a speech is done by one area, walking is controlled by another area, but they are not physically near, but still it is coordinated. How it is coordinated? Because there is connections between this. They are not physically near, but there are connections. Okay. So that is the functional connectivity, how the functions are correlated. And effective connectivity is the combination of these two. Now, can you think of a situation where some work which cannot be done simultaneously? Yes, that is the thing. If for Malayalis, I can tell you, there was a film called Pranjiyatan. In Pranjiyatan, it was asking, can you make the right leg in right direction, and you write 6 on the air. So do it simultaneously. Actually, it's very difficult, because these two things, muscle coordination and writing 6, that is coordinated by different areas and they have very little connection between them. So to do that, you should have so much concentration and you should have much expertise, and your neurons should be developed, connected, all those things should happen. So functional connectivity is very much important in this neuroscience. And we always, whenever we look for diagnosis, we look for the functional connectivity connectome. See, since there are 3 types of connectivity, there are 3 types of connectomes also. You have the structural connectivity connectome, and functional connectivity connectome, and effective connectivity connectome. But FCC is the most important one, that is functional connectivity connectome. So how the regions are connected to other regions by way of functions. Okay. But the proof of that is the functions, they correlate. So our challenge in this area is to learn the topological metrics, or you define new topological metrics which will correspond to biological mechanisms. So this is just an idea of fMRI, what is happening over there. See, in EEG, the electrical symbols, they are take that electrical symbols impulses by this impulses are converted into a matrix, and matrix is converted into a sparse matrix, then converted into graph. In this process, not all the people are involved: neurologist, neuroscientist, biotechnologist, computer scientist. All of them should work together to get a graph like this. Okay, so it's not that easy. Now, what are the parameters in brain networks which will help? The first one is centrality measures. It is based on the degree which quantify the wiring cost. Example is betweenness centrality, degree centrality, eigenvector centrality, all those things. The second is functional integration measures. It will measure the global connectivity depending upon the path length, all those things. Then you have the segregation measures. It is the local connectivity, or it is also called clustering coefficient. I will tell examples later. And then you have the resilience measures. Nothing much has been done on these resilience measures. Centrality measures, integration measures, and segregation measures, some work has been already done, but nothing much. I haven't seen any work in resilience measures. Resilience measures means what will happen if some edges go out, or if some damage happens to some edges, what will happen? What will be the result in the that patient? Now, there are some metrics which are computed using graph theoretical techniques, that is node strength, connectivity, small worldness, that is a very important measure, modular structure, hubs and centrality. Now, example to first centrality measure is between a centrality. I am taking example from each measure. That is, it is used to investigate the contribution of each node to all other nodes on the shortest path. It measures not only the importance of the node, but how they send, or how the information is sent between the node. Another one is average path length. It is the minimum number of edges that must be traversed to go from one node to another. So this is the definition. Li equal to sigma Dij divided by Ni minus 1, where Dij is the distance, shortest path distance matrix, and L is the average path distance graph. L is the, this is the average path length. This is the average path length. N is the number of vertices. Next idea is motifs in graphs. What is motif? Motif is a subgraph with a particular topological configuration. Just a subgraph, you can think it of as a subgraph. There are different types of motifs. Node motifs are there, edge motifs are there. Node motifs means which is at the level of a subgraph. Other one is the, it will measure how the information flow. So the aim of the motif analysis is to determine which specific node or path recur in network with a frequency that it is significantly greater than chance. So we have already, we have the first connectome which was developed was that of C. elegans. In the C. elegans connectome, they identify that triangular motif occur more frequently than any other motifs. So in brain, it is believed that triangular motifs, it is more frequent than other subgraphs. Why it is like that? Why can't complete graphs occur there? So if the brain graph is a complete graph, it's very well good, everything is connected. Why? What happened? What is the problem? There is no completeness in brain. It's because if to have a complete graph, you should have more edges. More edges means more cost. So you need more energy. So in energy wise, it is not economical to have a complete graph, for the brain graph to be complete. So our body itself, it has an optimal way of doing that. The connections are done in such a way that all the functions will be done, and it is economical in terms of energy. So in an undirected network, a triad of nodes can be connected in two ways, either an open triangle or a closed triangle. But if it is a directed network, there are 13 possible ways of connecting three nodes. These are the 13 possible ways of connecting a triad. In that, this motif which is called M39, this motif is most frequently occurring in brain network. Okay, it is proved with the help of C. elegans network and Drosophila network, all those things. This is the one which is more frequent in brain network. And regarding to that, there is one concept called clustering coefficient. That is the third segregation measure. Clustering coefficient is a prominent feature of nervous system. It was understood that in a paper by White et al., it was understood that C. elegans, the clustering coefficient or the triangle motif is more, occurs with more frequency. So triangular motif has something to do with neuron structure. Now what is clustering coefficient? Clustering coefficient is the measure of triangular motif frequency. Clustering coefficient is a measure of triangular motif frequency. It is the average of the clustering values of each nodes. And small worldness is the next segregation measure. That is, it is the ratio of clustering coefficient to average path length. And if this value, if this clustering coefficient and small worldness, if this value, these two values are very important in neuroscience. If this value is greater than 1, it is the indication of a small worldness. This small world property is not only seen in brain networks, it is seen in other networks like social networks, say web graph, all other networks also small world property is seen. You may have heard of this idea of 6 degrees of separation. So 6 degrees of separation means in a web graph, you need at least only a path length of 6 to reach one vertex to other. That is a 6 degrees of separation, the idea of 6 degrees of separation. Now it is reduced to 5, I think. I'm not sure about that. So small worldness is a property which is seen in networks generally, especially in brain networks. So clustering coefficient and small worldness, these two metrics are very much important in neuroscience. And how is it important? We'll see. So high clustering means tight integration and specialization within subsystems. And low path length means allows efficient integration with the specialized processes. So small world topology supports the emergence of, so in a brain, so you don't have complete networks, but you have something which have clustering, which have a optimal clustering coefficient and optimal small worldness. So these properties are together. So looking at the value of clustering coefficient and small worldness in the MRI or EEG or the connectome or functional connectome of a person, you can identify the whether he is a whether he suffers from a disease or not. So you can compare the clustering coefficient and the small world coefficient of a healthy person to one having or suspected to have Alzheimer's disease or Down syndrome or something like that, or schizophrenia. For all these diseases, see, healthy persons, then Alzheimer's disease, Down syndrome, schizophrenia, all these, if you look at if you compare the clustering coefficient and small worldness, you will get the idea what is happening over there. Okay. So in this paper is identifying discriminative features of brain network for prediction of Alzheimer's disease using graph theory and machine learning. So what is done there is that it is the prediction of AD. AD means Alzheimer's disease. It is a progressive neurological condition that affects millions of people. And what are the symptoms? It is cognitive decline, memory loss, behavioral abnormalities. The problem is that this happens mainly due to aging, and we are not these symptoms, when these symptoms occur, very slow symptoms is there. So when we occur for the first time, we will not identify that it is this. But if you are able to identify this AD in the earlier stage, it is manageable. So you can have a better life than if it is detected in the later stage. So detection or diagnosis is very important. And what is the usual way of diagnosis in now is there are some tests called neurophysiological tests and biomarkers such as cerebrospinal fluid. Cerebrospinal fluid is the fluid in the spinal cord, and amyloid PET imaging. All these methods are very expensive and they are invasive. They are invasive means they hurt us. You have to take the blood or sample or something like that. So it hurt us. So they are invasive and expensive. So we should look for an alternative diagnosis procedure. And in this paper, they have attempted to apply the threshold from the binary networks, FC binary networks. FC networks means functional connectivity network, and computed the graph metrics and graph metrics like small worldness, clustering coefficients, all those things, and used and they compared it with the data set of healthy patients, aging individuals, AD patients. These the three were obtained, and they compared it, and there was an indication when the clustering coefficient change or the small wellness coefficient change, there will be an indication for AD. And this is another paper, application of graph theory in identifying connectivity patterns. And all these papers are done by neuroscientists, and none of them is by a mathematics person. Recently in Chennai, I think in IIT Chennai, one paper was there. That paper was combinedly written by a biotechnologist, a computer scientist, and a mathematician. So if you want to do something here, you need to know our area. You should know what is graph matrix, or you should develop some graph matrix which is useful, which will be useful in their area. For that, you should know what is happening over there, and then you should try to do that. Now this was the first, Spons was the first person to introduce graph theory into neuroscience, and this is a very important paper by Spons, which came out in 2018. And this is also one. All these are in neurophysiology journals, not in mathematical journals. These are my references. This is very good book which is written in terms of graph theory. They have gone through all most of the metrics which is already developed, and how it affects the neuroscience. So fundamentals of brain network analysis. This is another one, and I have referred this one also to learn biology. And these are my references. I don't have any published work here, but I am doing something in centrality measures, especially stress of a graph. So I'll tell you this paper. This is the paper which I told you, it came out in 2021. Groups and leverage centrality and its applications in brain networks. Here there is a person from mathematics field. And the challenges is using graph theoretical techniques to learn more about human brain, predict and warn about the diseases like Alzheimer's, Down syndrome, examining fMRI, EEG, etc. using graph theoretical tools. And brain is a seat of all thoughts and emotions, and the gratitude is the healthiest of all emotions, and people who feel gratitude have higher volume of gray matter in their brain. So to have a healthier brain, let me express my sincere gratitude to Christ College and the faculty for having me here. Thank you. And also I would like to mention one thing. I was very happy to be here because my sister, Dr. Seena Verghese, is working in this department.
Thank you, Seema Chechi, for that wonderful session. Any questions from the audience?
In neural network, on which basis you are clustering the nodes as a single node?
It depends upon the situation, because suppose we are looking at the functional connectivity, or if you want to coordinate the coordinate some activities, then the vertices, selection of vertices, it depends upon what we need. Okay, so if it is about memory loss, so the region of memory will be one vertex of sure, and some others will be vertices. So each and every area has they will define a threshold value, and depending upon all the area which attains that threshold value will be considered as a vertex.
Okay. So what about that vertices in that cluster?
That everything will be considered as one. One
Okay.
vertex. That is, if frontal lobe, if you are looking at frontal lobe will be considered as one vertex. And this, you see, this is not a thing which, it is not like we are drawing the frontal lobe. Frontal lobe is not like that.
Okay.
It is, everything is connected only. It's a living organism, no? So everything is connected. So you cannot distinct like that. But you will, for the sake of doing something, we are making a distinction that if this area attains the threshold value, it will be considered as that vertex.
Okay.
That's a very, that's a challenge in this area, identifying the vertices.
One more comment is there. You are clustering vertices there. So that is also related to hypergraphs.
Hypergraphs, there are some works related to this using hypergraphs. The neuroscience is using hypergraphs also. That is, some papers recently I have seen some papers.
Yeah, I read one paper that is from PNAS journal, which is very famous journal, about network component analysis.
Okay.
So that idea can be used to study brain networks. Network component analysis.
Okay.
That is next step to principal component analysis.
Okay.
Yeah.
That may be.
Okay.
I have one more. I have seen a recent paper. Whenever there is changes in the brain, that can be studied. So there is an attempt to study the FCC, that is functional connectivity connectome, during menstrual cycle. That's a recent idea.
Yeah.
So what is happening over there? Before that, after that, what is happening in the brain? To study that, there is an attempt. So very interesting topic in this. But it's not that today or tomorrow you will go into publish a paper. It's not like that. I have been reading this topic since from 2020 onwards, COVID time I have been reading. And only after 4 or 5 years I was confident enough to give a talk.
Yeah, that is very difficult work actually.
Yeah.
Before my PhD, I started to work on this area with Professor Shekhar Mandi, who is director of CSIR, Government of India. But for this work, we need some statistics people, computer people, mathematics, and then biology people.
Data is also not easily available. Medical data. You need to compare FCC of healthy patient, AD patient, healthy person, AD patients. All you need data from the. So data is not easily available. That is a limitation of this area.
Microarray data is available there.
Yeah.
But to handle this is very challenging. But this is wonderful area to work for research, new researchers. Thank you. Thank you for the nice presentation.
Thank you.
Any further questions? So I think there are no further questions. So as the speaker mentioned, for a healthier brain, let us thank her for the wonderful talk.
Now I request Professor Aparna Lakshmanan to honor the speaker and Professor Seema Varghese to accept our token of gratitude. Thank you, Aparna ma'am and Seema ma'am.
Let us now start with our next session. The next session was originally scheduled to be conducted by Dr. Krishnan Paramashivan. However, due to an unforeseen emergency, he was unable to join us and we had to cancel his session. We are truly grateful that Professor Aparna Lakshmanan ma'am graciously agreed to step in at the last minute and share her valuable time and expertise with us. Our department is deeply indebted to you, ma'am. And it is with sincere appreciation and respect that I warmly welcome you as a resource person for today's session. I would also like to extend a warm welcome to Professor Thamar Shelvan T, who will be serving as the chair for this session.
Sir, 1 minute please. I would like to say some few words. With immense pride, we can say that we are here on the 3rd International Conference just because of Aparna ma'am. Because actually we are planning in 2023 International Conference, our new appointment. Dr. Seema Varghese lead the conference and Aparna ma'am was there throughout the conference with us and it was a great success. As all of you know, conducting or starting in an international conference in first time is a great task. Because the first event always sets standard for the future events. And that first conference was a great success. And I proudly and with heartfelt gratitude, I welcome Aparna ma'am to this talk.
So I am indeed very happy to be the part of this emergency event. So we thank on behalf of the organizers for the right now accepting that. I know Professor Aparna Lakshman very quite some time, maybe 20 years, but it is formally the job of introducing. And she completed her undergraduate from this soil, Irinjalakuda, from St. Joseph College in 2000, and subsequently she completed masters from CUSAT, Cochin University of Science and Technology, of course with the first rank in that batch. And subsequently she completed her PhD from CUSAT under the guidance of Professor Ambat Vijay Kumar in 2009. And initially she started her career in St. Xavier's College, Women's College in Aluva, and till 2021 she was serving there, and subsequently she moved to CUSAT. Alumni moved to the institution as professor in 2020-21, and she has been continuing there with the active involvement in teaching, research and other activities. And she has been operating research projects funded by reputed agencies, and she has conducted several conferences, of which the important are National Seminar on Graph Theory in 2014, International Conference on Recent Trends and Graphs Networks 2017, Research Discussion on Graphs and Groups in 2021. Of course, out of my experience, I attended quite number of events during COVID, but this program has attracted good number of intellectual and experts in that field, and the effect is still going on. And of course, the interaction with Peter Cameron, we started little bit earlier, but during the program it was quite progressive. And she arranged international webinar in honor of Professor Lovas, and she has been conducting Professor Ambat Vijay Kumar endowment lectures. And she received several recognitions, including Kerala State Young Scientist Award in 2012, IMS Prize in Discrete Mathematics in 2013, Best Alumni Award from St. Joseph College 2019, and the NTPL Enthusiastic Award in 2020. Of course, she has visited several countries, including Taiwan, Brazil, Slovenia, UAE, and she has been active researcher in graph theory in the fields like domination parameters, graph operators, and labeling problems. I am indeed very happy to invite the speaker for this session, please.
Thank you, sir, for that very broad introduction. Usually when I am part of the organizing team for a conference and I am delivering a talk, I have a hand on who is going to chair my session, and I see to it that it is very shortened. But here I am trapped. I can't say anything to Tamil Selvam sir. As he mentioned, he know me from, I can be more specific, he know me from 2004 December, when I started my research career in graph theory under the guidance of Professor Ambat Vijay Kumar. So it is 21 years long relation. He know me as a student, so I can't control him. In fact, he can control me, that is it. And as you will be knowing, I'm here as an accident. Sometimes accidents are happy accidents, and this is the consequence of an unhappy accident. Happened to a relative of the resource person. So sometimes unhappy things happening somewhere becomes happy thing for someone else. So everything is relative, very much like mathematics. And here, in fact, I didn't start from home to this college thinking that I'm going to deliver a talk. I have have given so many talks in this auditoriums, and Vijay Kumar sir and myself were very particular that for this this conference, I will not serve as a resource person. We need new faces, so I will not serve as a resource person. I will just come on one day just to give moral support to the organizers, but I will not give any talk. That was the decision from one of the main organizers, Ambat Vijay Kumar, and yeah, he decided that after discussing with me. But destiny says that I must give a talk, so I am again here. And when I started from home, I was not planning to give any talk, so I can have the advance bail that this is not a prepared one. Luckily, I had my laptop with me, and many of you, like me, are teachers, and we can teach whenever we get a free PT period, right? That is what the people say about mathematics teachers. Whenever there is a free period, a mathematics teacher will be there. So yeah, I am here, believing in my brain. Okay, so I'm planning to deliver a lecture related to general position and mutual visibility problems in graphs. This is joint work with Professor Sandy Clauser and Dhanya Roy. Dhanya Roy is currently doing PhD under my guidance. The basic problem starts from the classical no 3-in-line problem. The classical no 3-in-line problem is like you have an n by n grid. You are supposed to place points in the grid in such a way that no 3 points are in a straight line. When I say grid, you should not get confused with the graph theory notion of a grid. For us, grid means it is path, Cartesian path. Here you can see that it is not used in that sense. In this structure, you have to place points in such a way that no 3 of the points are in a straight line. Not in horizontal, not in vertical, and not diagonally. So here you have an example of a 3 by 3 grid. You can see black points. And it is easy to verify that no 3 of them lie in a straight line. But is this going to be the best possible? Can I place a 7th point? The answer is no, because there are only 3 rows and 3 columns. You can have at most 2 points from a row. So this is going to be the best possible. And from a 3 by 3 grid, the best possible is 6. In general, this is still an open problem. That is, given an n by n grid, how many points you can place in the, say, in graph theoretical terms, in the vertices, or how many vertices you can choose in such a way that no 3 points lie in a straight line. So given an n by n grid, this is still an open problem. 2n is an obvious upper bound because there are n rows and n columns. From a row, you cannot have more than 2. So 2n is an obvious upper bound. Here it is attained, but as n grows, we are not sure that will it be possible to place 2n. If you have a realization where you can place 2n, then we are done. This is going to be the best possible, but the problem is still open. And this problem is due to Dutney, and this is posed in 1917. Exactly 100 years after this no 3-in-line problem, say a generalized version of this no 3-in-line problem was posed in 2017 due to Froeses. In the original problem, we were considering a grid, and we were trying to place points in the corners of that grid. Why a grid? You are given a plane. In that plane, you have to place as many points as possible so that no 3 of them lies in a straight line. So the question was extended from grid to a general plane. In that general plane, you are given a set of S points, need not be in the shape of a grid. A very large collection of S points are there. You have to choose a subset S dash from these points in such a way that no 3 points again lies in a straight line. Immediately after this extension to the plane, in 2018, Paul Manuel and Sandy Clauser extended it, a graph theoretic version of the same was introduced. As you can guess rightly, instead of a plane and a set of points, we are considering a graph G. And we are considering a largest set S of vertices of G such that no three vertices lies on a common shortest path. The major problem when extending this from usual geometry to graph theory is that when we are considering usual geometry with usual metric, the shortest path connecting any two points is a straight line, and that is unique. So no 3 points lie in a straight line makes sense in the way that when two people want to communicate, there should not be a third person in between, the shortest path being the straight line connecting them. But when coming to graphs, as you know, between 2 points we have n different paths, and you may consider only the shortest paths, or you may consider all sorts of paths. So when extending to graphs, what should be the criteria? Should we go for shortest path alone, or should we consider all sorts of paths? And again, the shortest path is not unique. In plane, the shortest path is a straight line which is fixed. But when coming to graph theory, even when we are restricting ourselves to geodesic paths, shortest paths between 2 points, the shortest path need not be unique. So how to do that? In the problem, in the way Paul Manuel and Sandy Clauser suggested, they were considering all shortest paths between every pair of vertices. So you are looking for a set yes such that you take any two vertices from that set yes and consider all shortest paths connecting these two vertices. A third vertex from S should not be an intermediate vertex. So this is the way Paul Manuel and Sandy Clauser extended the problem to graph theory, and in that paper itself it was proved that finding such a set is an NP complete problem, and obviously we are trying to maximize the number of points. You can always find, you can just go for one single vertex, so there is no question of a third person coming in between. You can go for two vertices, so there is no question of a third person coming in between. So finding a set of vertices which is in general position is not tough, but maximizing the cardinality of a general position is what makes it tougher. Okay, so this is the formal definition. A set of vertices G is in a set S of vertices of G is in general position if no three vertices of S lie in a common shortest path. And GP of G denotes the general position number, which is the cardinality of a maximal general position set. And a general position set which attains this maximum value is termed as a GP set. So here you have an example. You can see that the black dots. So you can see that from this graph I have taken 3 black points. There is only one shortest path connecting these 2 points, it is clear. And from this vertex to this vertex I have 2 shortest paths, one through left side and the other through right side. Both paths are clear. So this is an example of a general position set, and this is maximal in the sense that if you try to add any one more vertex to the collection, you can see that at least one shortest path is blocked. But the general position number is not 3. You can replace this lower black vertex with these 2. I am making these 2 as black and changing this to white. Then again you can see that the set is in general position, and that is going to be the best possible. So the GP number of this graph is 4. The figure only illustrates a set which is in general position, which is maximal but not maximum. Okay. So as in the case of other minimization, maximization parameters like domination, independence, etc., there could be sets which are maximal but not maximum in the case of general position also. And as I already pointed out, when Sandy and Paul Manuel extended the notion to graph theory, they were considering all shortest paths connecting every pair of vertices in S. For communication, we need only one shortest path. No need to consider all shortest path. If one path is clear, we can communicate through that channel. It's not necessary that all the channels are clear. So that gave a weaker notion of general position termed as mutual visibility. Say two vertices are said to be mutually visible given a graph G and a subset S of the vertex set. It is said two vertices are said to be S visible if there exists a shortest path from U to V in which there is no third vertex from S, which is clear. Okay. So then we say that this U and V are S visible. If every pairs of vertices are S visible, then that set is called a mutual visibility set. So this extension was suggested by Gabriele Di Stefano in 2022. Still, the problem is NP complete. We have reduced the hardness. In terms of definition, we have reduced the conditions, but still, the problem is NP complete. And this is the technical definition. A set S of vertices of G is a mutual visibility set if every pair of vertices in S are S visible. And the mutual visibility number is the maximum possible size of a mutual visibility set of G, and it is denoted by mu of G. And a mutual visibility set which attains the cardinality mu of G is called a mu set of the graph. Here I have taken the same example and I have chosen a mutual visibility set which is not in general position. Say you can see that from this black vertex to these two black vertices, we have a shortest path through the left side which is blocked. So this collection of black points is not in general position, but I have another shortest path through right side. So one shortest path is there. For every pair of vertices, you can see that at least one shortest path is there. So this is a mutual visibility set which is not in general position, and this is going to be the best possible. So mutual visibility number of this graph is again equal to 4. Okay, this is one application side. In mobile entities while communication is made. Sometimes you can see that, especially if you are using a BSNL network, sometimes you can see that when two people are talking to each other, in between suddenly we'll start hearing the conversation of some other people. Okay, so some network clash is happening there in between. So to avoid that, to avoid such things, this mutual visibility has a major role. Okay. And here I have given the value of general position and mutual visibility for some simple classes of graphs. For path, what happens is that if you take any three vertices in path, there exists only one shortest path connecting two vertices. So if you take any three vertices, one vertex will be in the middle of the other two. Whichever three vertex you choose, one vertex will be in the middle of the other two. So for path, the general position number as well as the mutual visibility number is going to be 2. For cycles, when you are considering C4, for general position it is 2, whereas for mutual visibility it is 3. Again for starting from n greater than or equal to 5, for all n it is going to be 3. General position as well as mutual visibility is going to be 3. So when we are considering bigger cycles between two vertices, if we choose it wisely, we can have one shortest path through clockwise direction and another path through the anti-clockwise direction. So if we choose wisely, we can place 3 vertices so that the shortest path do not intersect with the third vertex. So both general position and mutual visibility are equal to 3. When we are considering a cycle. And when coming to complete graphs, the question is too obvious because between every pair of vertices there exists an edge. So the shortest path is an edge. So a vertex cannot come in between. So I can go for all the vertices. I can take all vertices to the general position set as well as to the mutual visibility set. So both these parameters are equal to n. So you may get a feeling that most of the times this general position and mutual visibility are going to be equal, but that is not the case. The difference can be arbitrarily large. The simplest example being the complete bipartite graph. In a complete bipartite graph, if I am taking 2 vertices from a partition, then all vertices in the other partite set is in a shortest path connecting these 2 vertices. So if from a partite set I am taking 2 vertices, then from the other parted set, I cannot take any vertex. But okay, I can go for choosing all vertices from one parted set because the shortest path is through the other parted set. So general position number is the maximum of m and n in that case. But while coming to mutual visibility, I need only one clear path. So I can choose all vertices except one from both parted sets so that one shortest path is always clear. So that can go up to m plus n minus 2. So mutual visibility is m plus n minus 2, whereas general position is n. So the difference is m minus 2. So this m and n are arbitrary, so the difference can be arbitrarily large. When coming to trees, there is a kind of argument, say, which we call as pushing argument. If we are taking a general position set, I can always push the vertex which has chosen to the leaf vertex, to the pendant vertex, keeping the property of being in general position. This is not a logical or mathematical way of arguing it, but that can be proved. It is known that the general position number of tree is the collection of all leaf vertices, and for mutual visibility also the same thing happens. In fact, when you are in a geodetic graph means there exists a unique shortest path between every pair of vertices. The shortest path is unique for every pair of vertices. So when you are in a geodetic graph, obviously general position coincides with mutual visibility. General position insists that all shortest paths must be clear. In geodetic graph, there is only one path, and mutual visibility say that at least one must be clear. So when we are restricting ourselves to geodetic graphs, obviously general position coincides with mutual visibility, and trees are a subclass of geodetic graphs. So general position as well as mutual visibility is equal to L, where L is the number of leaf vertices in the tree. And these are some very basic results related to general position and mutual visibility. An obvious lower bound could be 1, but one may think that if there is at least one edge, then I can choose 2 vertices, right? But K1 is also there. So that is why the lower bound is kept as 1. Otherwise, I can say that it is 2. Okay. So 1 is an obvious lower bound for general position, and the maximum that we can go is up to n. And 1 is only for K1. For GP as well as mu, the value is 1 only for K1. And GP equal to 2 is also characterized. It is true only for path for n greater than or equal to 2, and for C4. Again, equal to n is also characterized. For other values, say given a k between 1 and n, characterize all graphs which attains GP equal to k, or even mu g equal to k is an open question. For 1, 2 and n, the problem is settled. For n minus 1 and n minus 2, I have seen a paper in archive. I haven't gone through the proof given in that paper, and that has not yet been accepted for publication. So we can't say that the problem is settled, but I think that someone has settled the problem. I haven't gone through the proof yet, so I'm not sure, and I haven't included that in the presentation. But if you are going to try anything related to this problem, make sure that you see that paper also, where they claim that they have settled GP equal to n minus 2 case, and another paper in which they have claimed they have settled GP equal to n minus 1. For other values, I'm sure that still this problem is an open one. Now, I told that for geodetic graphs, GP of G equal to mu G. But what about the converse? If the graph is not geodetic, can you say that GP and mu are different? Again, it is not true. Example being even cycles. Even cycles are not geodetic in the sense that diametrically opposite vertices have 2 different shortest paths. So even cycles are not geodetic. And for n greater than or equal to 5, I already mentioned that both GP and mu are equal to 3. So even cycles serves as counter example for converse being not true. And there are some other parameters originated from this mutual visibility as well as general position. In mutual visibility, what we say is that there must be a clear vision between any two vertices in the collection, yes. Say, let us assume that we are going to place robots in a network in such a way that two robots must be able to communicate with each other without a third robot coming in between. Okay, so when you are going to maximize, what you are going to find is a mutual visibility set. But what if there are robots placed at different vertices, and at other vertices, some human beings are there holding a remote. They need to control these robots with their remotes. When they are trying to give a command to a robot using their remote, a second robot should not come in between and catch this command. Okay. So visibility is to be there between every pair of robots so that they can communicate with each other, and between human and robot. Okay, so that must be possible. So that is the motivation behind introducing outer mutual visibility set. A set S of vertices of G is an outer mutual visibility set. If S is a mutual visibility set and every pair U element of S and V element of S complement are also S visible. So the vertices in S must be visible to each other. Apart from that, vertices in S and vertices in S complement must be visible to each other. So a condition is increased. Okay, such a set is called an outer mutual visibility set denoted by mu naught of G, and the set which attains that value is called a mu naught set. So this is one variation of mutual visibility set. Another variation is total mutual visibility set. Here the thing is that robots must be able to communicate with each other, human must be able to communicate with the robot, and humans must be able to communicate with each other without a robot coming in between. So you are going to find a set S such that every pair of vertices are S visible. Let the vertices be from S or from outside. Every pair of vertices must be S visible, and that is the notion of total mutual visibility set. Again, it is denoted by mu T of G, and the set which attains that value is called a mu T set. So here you have an example of a graph. This black vertices denotes the mu naught set, and in B you can see a mu T set. Okay. Unlike mutual visibility and outer mutual visibility, this total mutual visibility number could be 0 also, because if every vertex is the central vertex of a convex P3, then between the end vertices of that P3, the unique path passes through the central vertex. So if I am considering a graph G in which every vertex is the central vertex of a convex P3, then mu T can be 0. And which graphs attains mu T equal to 0? The characterization is already done. That is what I just told. A graph G has mu T of G equal to 0 if and only if every vertex is the central vertex of a convex P3. And can anyone say any example of a graph for which every vertex is the central vertex? Will that ever happen? Yes, cycles. If you take cycles of length n greater than or equal to 5, you have to specify that n greater than or equal to 5. Okay, if you are taking a C4, it's not true. Say from V1 to V3, it's not, unique path is not through V2. We have V4 also. Okay, so for C4 it is not true. For cycles of length greater than or equal to 5, you can see that every vertex is the central vertex of a convex P3. So for that graph, mu T can be even 0. Okay. Yeah, I have some more time left. So before going to that, there is another variation. As I told, these slides were not prepared to talk for 45 minutes. These slides were prepared for a talk for 30 minutes. But still I have some time. Though the contents are not there in the slide, I can speak. Okay. And there is another notion called dual mutual visibility number. Dual mutual visibility states that every pair of vertices in S must be S visible, as well as every pair of vertices in S complement must be visible. There is no question of human communicating with robot. Robots must be able to communicate with each other without a robot coming in between, and humans must be able to communicate with each other without a robot coming in between. So that is the notion of dual mutual visibility, which is denoted by mu D. And related to this mutual visibility parameters, there is a notion of coloring also. What is usual coloring? Usual coloring means you have to color vertices in such a way that no two adjacent vertices receives the same color. But in fact, what you are doing is you are partitioning the vertex set in such a way that each partate set is an independent set. That is what you are doing when you are doing the usual coloring. So here what we insist that we need to color the vertices of a graph in such a way that each partate set is a mutual visibility set, or say each partate set is an outer mutual visibility set, or say each partate set is a general position set. So when you are doing such a coloring with least number of colors possible, we get a coloring version of general position as well as mutual visibility as well as other parameters. I just mentioned 4 variations of general position. There are other variations also for general position also, this outer general position, dual general position, and then one more total general position notions are there. Apart from that, there are other variations also, say like k distance mutual visibility, k distance general position, such variations are there. For 3 or 4 variations, this coloring parameter has already been introduced and studied with a few publications in that direction. But for other parameters, this question of the corresponding coloring is a new area, is an unexplored area. So any researchers who are looking for problems, here you have, say, 10 problems. You have 10 variations of general position and mutual visibility for which the coloring has not yet been explored. So with that I am concluding. These are some of the papers which came out of our work related to mutual visibility and general position. The first one is published in Applied Mathematics and Computation, mutual visibility and general position in double graphs and in Miesel skin. In the first talk today, you have heard about the definition of Miesel skin of a graph. So we have explored what happens to the mutual visibility and general position parameter when the operator of Miesel skin is applied, as well as when the operator of double graphs are applied. And this is already a published work which you can find in the website. And this is our second paper in that direction, counting largest mutual visibility and general position sets of glued binary trees. Here what we have done is that for glued binary trees, generalized glued binary trees, glued T-array trees and generalized glued T-array trees, we have not only evaluated the value of the parameter, but we have actually counted how many GP sets are there and how many mu sets are there. So completely done in the sense, and this paper was communicated to results in mathematics, and yesterday we received the notification that our paper has been accepted for publication. Since this was a surprise talk, I didn't get time to edit my slide. So this you can find shortly in results in mathematics. Yesterday only we got confirmation that the paper is accepted. And this is a third paper where we study the mutual visibility problems. All 4 variations of mutual visibility parameter in the case of Sierpinski graphs. We have found the exact value of mutual visibility number of Sierpinski graph, mutual visibility as well as the other 3 variations, and this paper has been communicated to discrete mathematics, discussions mathematics and graph theory, result awaiting. Okay, so I'm not sure, but you can find it in archive, and these are my references, where you can see the first papers in general position as well as mutual visibility and the previous literature related to that. Another set of references. Third set of references. Last one. Thank you.
Any observation or questions or anything?
thank you. I just want to thank you for your nice presentation.
Thank you.
You motivated all these concepts very nicely. And just one question, you mentioned graph with where a general position number is equal to the number of vertices minus 1.
Yes.
Some new paper.
Yes.
Can you say something about these graphs with this property?
Oh, I'm sorry that I don't remember what they have, what the characterization actually says, but if you are interested, I can just find that paper and send it to you.
Okay.
I just don't remember that. As I already told, I was not prepared for this talk, but I have seen that one.
Okay.
I just remember that I have seen that one.
Okay, thank you.
Yeah.
Anybody else?
So I'd like to
Okay.
add one thing at this
Yeah,
point.
please.
When Tamil Selvam sir finished his talk, so many questions were coming. So Karthik was mentioning that the talk was well received, all of them understand, that is why they are asking questions. But now I can see that there are no questions, but I would like to tell him that the converse is not true.
Yeah, that is what I would like to tell.
I believe
Maybe
that
the
all-
reason is too elementary.
Yes, yes.
So that is also the things are there.
I
But
believe that all of you
Okay.
understood everything and hence there are no questions. Okay, thank you.
there are so many parameters for the tit factor. Okay, we are very thankful to the speaker for the nice talk on the topic. So we thank you once again. Thank you.
Now I request Professor Tamil Selvam T to honor the speaker and Professor Abarna Lakshman S to accept a token of gratitude.
Good afternoon, everyone. I take few seconds to express my sincere gratitude to our dear Abarnama. My sincere thanks to dear Abarnama for being with us and the unwavering support given at such a last moment. Your humanity in accepting our invitation in this last moment is truly means a lot to us. On behalf of the Department of Mathematics and as a convener, I express my sincere gratitude to dear Abarnama. I also express my thanks to Professor Tamil Selvam sir for sharing this session and for being with us. Thank you.
As we wrap up the morning sessions, now it's time to refuel. Let's take a lunch break. Remember, this is also a great opportunity to network and share thoughts with each other. I request everyone to be back.
Welcome back, everyone. I hope you all enjoyed your lunch and had some time to recharge. Next is an online session. The speaker for the session is Professor Stephen Wagner. He will be discussing the topic Maximal Independent Sets in Twin Free Graphs. The chair for the session is Dr. S. Francis Raj. I kindly invite Dr. S. Francis Raj to chair the session.
So shall we start? Yes? Okay, fine. So I welcome everybody for the afternoon session. The session is going to be given by Professor Stephen Wagner. So I don't know, maybe, sir, you are able to see me?
Yes, now I am.
Yes. I don't know, maybe you remember or not, we met in Erode also 2 years back in a conference. So it gives me great pleasure in inviting you or telling a few words about you. So Professor Stephen Wagner, he finished his PhD from Graz University, Austria in 2006, and then probably went to hold positions in Sweden, South Africa, and then came back to Austria again. So from 2023, he has been a full professor there. His area of specialization is combinatorial probability, enumerative and analytic combinatorics, and graph theory, of course. He has more than 160 publications in reputed journals. He has got 2 awards, one from the Royal Society of South Africa and one as an award for distinguished research from the, again, South African Mathematical Society. So with these few words, I invite him to give his lecture on maximal independent sets in twin free graphs.
Thank you for the kind introduction, and thank you for having me. It's my pleasure to speak in this conference. I will be talking about some recent joint work with Stein-Cambie on maximal independent sets, specifically the number of maximal independent sets in twin free graphs, as we will see. So to give you a little bit of background, first I should say what a maximal independent set is, of course. An independent set of a graph is simply any set of vertices with the property that no 2 of them are adjacent, like in the graph I've shown here. The 3 blue vertices form an independent set because no 2 of them are adjacent. Now, such an independent set is called maximal if it's maximal with respect to set inclusion. So there is no larger independent set that contains it. The independent set here in the example, with the 3 vertices indicated, is not maximal in this sense because I can add one more vertex. You can see that adding this additional vertex retains the property that no 2 vertices are adjacent, so I have a larger independent set containing the original one, meaning this vertex is not maximal since it's contained in a larger one, but the independent set that's shown here, consisting of 4 vertices, is indeed maximal. It's not possible to add more vertices to it while keeping it independent, because all 3 remaining vertices are neighbors of at least one of the blue vertices. So that's a maximal independent set. Equivalent to the notion of maximal independent is the notion of independent dominating. So an independent set is maximal if and only if it is dominating, meaning that all the elements that are not in the set are at least adjacent to an element in the set. That's the dominating property. All right, so now we will be mainly interested in the number of such sets. And this is actually a problem that has quite a bit of history. Already back in the 60s, the question came up, how many maximal independent sets a graph of order n can have? This was addressed in particular in 2 papers in the 60s, Miller and Mullen, 1960, Moon and Mercer, 1965, showing that the number of maximal independent sets in a graph of order n is at most essentially 3 to the power n thirds. So it depends a little bit on the residue class of n modulo 3. There is one case where n is divisible by 3, one where n is 1 mod 3, one where n is 2 mod 3. In each of these cases, we have an upper bound that is basically some constant times 3 to the n thirds. These upper bounds are reached with equality by graphs that are disjoint unions of essentially many K3s, many triangles, and at most two K2's components of order 2. That's in the cases where n is not divisible by 3. So if n is 2 mod 3, we need to add one such component, that's a K2, and if n is 2 mod 3, we have to add two components that are K2s to reach the upper bound. Now, one can ask what happens if the graphs are necessarily connected, because the extremal graphs previously were disconnected, were disjoint unions of K3s and K2s. This was investigated a bit later, 20 years later, by Furedi, and also Griggs, Grinstead, and Guichard, who showed that for connected graphs, there are similar bounds. The order of magnitude is still about 3 to the n thirds. And the construction is also quite similar. It's basically a lot of triangles that are connected together, and then depending again on the residue class of n mod 3, you have to do a bit more. So the blue vertices indicate what you might have to add depending on the residue class of n modulo 3. So if n is divisible by 3, then you don't need these blue vertices in your construction. If n is 1 mod 3, you need one of them. If n is 2 mod 3, you need both. So that's the construction that yields these upper bounds. Again, order of magnitude roughly 2 to the n thirds, growing exponentially with n. Now, for trees, the situation is a bit different, but still similar. The upper bound is basically 2 to the n half. So again, exponential growth, but with a different growth constant. So essentially, we're growing like 2 to the n half here. The extremal trees that have the maximum number of maximal independent sets, given the order, are these trees that are called spiders. They are not the only ones, as it turns out. There are other trees that reach the maximum, but the spiders are an equality case for these upper bounds. Okay, so we know quite explicitly what the maximum number of maximal independent sets is in a variety of graph classes. So we had it for arbitrary graphs, connected graphs, trees. So the maximum is quite well under control. Now, one might also want to look at the minimum. So what's the minimum number of maximal independent sets a graph can have? But generally speaking, this is quite easy, and there's not much to say about it a priori, because the star has exactly 2 maximal independent sets. That's actually true for any complete bipartite graph. Okay, so why does the star have 2 maximal independent sets? Well, the one is where only the center of the star is contained. If the center is there, then none of the neighbors can be. So that's an independent set and it's maximal. As soon as you have one of the leaves included in your independent set, then the center isn't included. And so to make it maximal, all the leaves have to be included. So that's the second possible maximal independent set that a star has. It's a set consisting of all the leaves. So there are only 2 maximal independent sets, the center alone and all the leaves. So that's just 2 maximal independent sets. And it's not too hard to convince yourself that if a graph has no isolated vertices, then it must have at least 2 maximal independent sets, because you can take any 2 adjacent vertices, start from one of the 2 vertices and extend until you have a maximal independent set. So the minimum is somewhat trivial. If you allow disconnected graphs, in particular if you allow isolated vertices, then actually the minimum is 1. If you take a graph without edges, that has just 1 maximal independent set. Otherwise the minimum is 2. It's 2 for connected graphs, it's 2 for trees. So there is really not too much to say about that. at the moment. In fact, for any integer k greater than or equal to 2, it's possible to construct infinitely many connected graphs that have precisely k maximal independent sets by using a simple observation, namely that if two vertices have the same neighbors, then every maximal independent set either contains both of them or neither of the two. Let me quickly illustrate this. So I'm showing you again the graph from before, and the blue vertices here, they form a maximal independent set. You see that they are independent and everything else is adjacent to at least one of the blue vertices. So here, V and W, vertices that have the same neighbors, namely these two, none of the two is contained. On the other hand, here is a maximal independent set that contains both of them. Again, 4 independent vertices, all of the others are adjacent to at least one of them. Now, could there be a maximal independent set containing only one of the two? The answer is no, because if, let's say, V is contained in an independent set, then neither of the two neighbors is. So to be maximal, W has to be contained as well. It would always be possible to add W otherwise. So if two vertices have the exact same neighbors, then every maximal independent set either contains both of them or neither of the two. And so whether or not we include W is really irrelevant for the number of maximal independent sets. If I remove W, I get the exact same number because V and W are either both there or not at all, so I can treat them basically as one single vertex for the purpose of counting. So that means as soon as I have one graph with exactly k maximal vertices, maximal independent sets, then I can get infinitely many more by just creating additional vertices with the same neighbors as existing vertices. So two of the vertices with the same neighbors will be called twins. So the two vertices V and W here in the example, they would be considered twins because they have the same neighbors. And the observation that I gave you earlier is that if we add or remove a twin, the number of maximal independent sets stays the same. Meaning that if I have a graph with k maximal independent sets and I keep adding twins, the number of maximal independent sets stays equal to k. It will not grow. Now we will be interested in graphs that do not contain twins. So twins, so twin-free graphs as we call them. Now as it turns out, for twin-free graphs, the question of what the minimal number of maximal independent sets is becomes more interesting, because suddenly it's no longer just 2 for all the graph classes, but we will see different behavior showing up. Just forbidding the simple construction of adding or removing twins makes the question for minimum a lot more interesting, as we will see. So for twin-free graphs, the problem of determining the minimum number of maximal independent sets is more interesting, as I will try to explain. We will see different behavior depending on which class of graphs we are considering. And the extremal graphs are also rather interesting and unexpected, at least to some extent. All right. So what do we get? The first step is to just consider arbitrary twin-free graphs, not imposing any additional restrictions other than being connected for the time being. So if I take a connected twin-free graph, then if I know that there are exactly k maximal independent sets, I have a bound on the number of vertices. Number of vertices is then at most 2 to the k minus 1 plus k minus 2. And there is a case of equality, and I will show it in a moment, that you reach if the graph is precisely a clique, complete graph of order k minus 1, with some vertices added. Specifically, for every subset of the clique, I add one vertex, whose neighborhood is exactly that subset. So if I turn things around, if I take the order of the graph as fixed, and I want to know how many maximal independent sets does the graph have at least, given that it's twin-free. So if I take these inequalities and turn them around, I find that the minimum number of maximal independent sets is logarithmic in the order. Right? So if I take the logarithm here, then basically I find that k needs to be at least roughly the base 2 logarithm of a. So the minimum number of maximal independent sets in connected graphs grows with the logarithm of a. Okay, let me illustrate the construction that yields the minimum. So I take a clique that's here, a clique on 3 vertices for the sake of the example. Then for every non-empty vertex subset, I add a vertex whose neighborhood is precisely that set. And then, as it happens for every vertex of the clique, there is precisely one maximal independent set that contains it. So we have exactly as many maximal independent sets as vertices in the clique, in this case 3, plus one more that consists of all the other vertices. I will illustrate this in more detail in a moment. So this is the construction, works for every fixed k, gives me a graph of order 2 to the k minus 1 plus k minus 2 that's connected and has exactly k maximal independent vertices, maximal independent sets. Here it is again, just a bit bigger. So I start with a clique on 3 vertices. That's the case where k is 4. So a clique of k minus 1 vertices, in this case 3. And then for every subset of these 3 vertices, for every subset of UVW, I add one vertex whose neighbors are exactly that subset. So for example, for the subset consisting only of U, I add this vertex, has only neighbor U. For the subset consisting of U and V, I add this vertex, it has exactly neighbors U and W. And so on. UVW, the subset of all the vertices, gives rise to this vertex that has all 3 of them as neighbors. So this is how the construction works. Start with a clique on a certain number of vertices, add a vertex for each non-empty subset. Now the independent sets look like this. So I've the first maximal independent set is this one, 4 vertices, 1 vertex of the clique. That's my clique. I take one of the vertices, and then all the others that are not neighbors. Right, this is a maximal independent set. It's clearly independent, and everything else is a neighbor. Second one is similar, just basically rotated. The third one is also similar, just rotated once more. And the fourth maximal independent set consists of all the rest. And it's not too hard to convince yourself that this is really all the maximal independent sets you can get, because at most one of the vertices of the clique can be contained in your independent set, and once I have decided which of them is contained, I know all the other vertices to include. Alright, so this is the construction that reaches the minimum. To show that this is actually the best we can do, so to show that the upper bound we're claiming on the number of vertices of a graph with k maximal independent sets really holds, we use a rather simple idea. In a twin-free graph, if I take any 2 vertices v and w, there has to be a maximal independent set that contains precisely one of the 2, that distinguishes them in one way or the other. Because I can find a vertex that's a neighbor of one of the 2 but not the other, otherwise they would be twins. Then I take this vertex, I include it, and of the 2 vertices v and w, include the one that's not a neighbor, and then I extend to a maximal independent set. What I get is a maximal independent set that contains one of the 2 vertices v and w but not the other. So there is always a maximal independent set containing precisely one of the 2. Meaning that I can distinguish any two vertices by knowing which maximal independent sets they're contained in. So every vertex is uniquely determined by the maximal independent sets it's contained. If I tell you for a vertex, these are the maximal independent sets it's in, I can uniquely define it. That means if there are k maximal independent sets, the most you can have is 2 to the k vertices, because that's how many subsets of maximal independent sets there are. There cannot be more than that. This is not quite the upper bound. The upper bound is 2 to the k minus 1 plus k minus 2, as I showed you earlier. But it's sort of similar, right? It's 2 to the k in essence. And to get the actual bound, 2 to the k minus 1 plus k minus 2, one uses basically this argument just refined a little bit further. This is really what goes into the proof. Okay, so we have established now that the number of maximal independent sets in a connected graph of order n is basically at least logarithmic in n. If I allow disconnected graphs, if I drop the condition of being connected, things do not change very much. You see that the most I can gain is one more vertex. So I can add one isolated vertex to the graph, increasing the order by 1, but that's really the best I can do. So all that has changed in the description of the construction is that I'm adding a vertex for every subset S, and the S can also be the empty set now. Otherwise, it's the exact same construction. It's still true even for disconnected graphs that the number of maximal independent sets in a twin-free graph of order n is logarithmic in it. Okay, so remember that. Twin-free graphs, number of independent sets, at least logarithmic in the size. Now what happens if I change things a bit, if I impose other restrictions on the graph? One natural thing to do would be to consider bipartite graphs. So if I take a connected twin-free bipartite graph, things change. It is no longer possible that the number of maximal independent sets is logarithmic in the size. It already has to be linear in the size. In fact, the lower bound here is basically n over 2. Rounded up and added 1, but essentially n over 2. Linear in the size. This inequality is sharp, and there are explicit constructions. So there are in fact many graphs that attain this bound. One possible construction is to take a balanced complete bipartite graph. Complete bipartite graph where the two partite sets are as equal as possible. And then you remove a matching of size n half minus 1 from that. I'll show you an example in a moment. So here is the construction, specifically when n is 6. This is one of the graphs that has the minimum number of maximal independent sets among twin-free bipartite graphs. Right. So you can check that this is indeed twin-free. No two vertices have the same neighborhood. And there are, as it turns out, 4 different maximal independent sets. One here is the set of 3 indicated in red here. The other one is just the vertices on the other side. They form a maximal independent set. And then there are 2 more. This is a maximal independent set. They are independent and everything else is a neighbor. And these 2 also form a maximal independent set. They're independent, they're not adjacent, and everything else is a neighbor of one of the 2. So also maximally independent. And you can check that these 4 are really all the maximal independent sets the graph can have. This illustrates the construction, and it works for arbitrary size. You just add more vertices on the left, more vertices on the right. And otherwise keep the construction basically the same. How do I know that this is indeed the minimum? So how do I know that a bipartite twin-free graph needs to have at least that many maximal independent sets? The argument is actually relatively short. We can actually prove something stronger. If we take a twin-free bipartite graphs, no isolated vertices allowed for the moment, so we want to keep them connected. and we take A vertices on one side, B vertices on the other, then the number of maximally independent sets is at least size of one of the partite classes. We can take the larger one of the two, plus 1. That's the absolute minimum we can have. Why is that? Well, for every vertex on the larger side of the graph, I can take the set consisting of everything that's not a neighbor of V on the left, and every vertex whose neighborhood is a subset of the neighborhood of V on the right. This is illustrated here. So I fix a vertex here on the right in B. That's the neighborhood. I take everything that's not in the neighborhood on the left, and then I take all the vertices on the right that only have neighbors here, but not there. Right, so all the edges go only into here, whereas these vertices have neighbors here and possibly also here. So these are not included. Only the red parts are included in my maximal independent set. So you can convince yourself that this is independent because, well, on either side, the vertices are not adjacent to each other because of bipartiteness. And then there are no edges between the two by construction, because we said that the vertices in this red block only have neighbors over here. They can't have neighbors here. So there are no edges going between this red bit and this red bit. It's really an independent set. And it's also maximal. I cannot include anything else because I would make it no longer independent, basically. So I have everything in here, everything here. If I were to include something in this bit, there would be a problem with vertices over here, because the vertices in this part, they have adjacencies over here and would create a contradiction. And likewise, anything here is a neighbor of V, so V is included in my set, so I can't have them in there as well. So this is a maximally independent set by construction, meaning that for every vertex here in B, I have at least one maximal independent set. And all these sets constructed are different from each other because my vertices have different neighborhoods, because I'm assuming my graph is twin-free. So all of these sets are different from each other. Because for any two vertices U and V, the neighborhoods are different, so these sets are simply not the same. All right, so that gives me at least as many maximal independent sets as there are vertices in B. And then I have one more maximal independent set that just contains all of A. I have at least number of vertices in B plus one many maximal independent sets. That's a clear lower bound, showing that the lower bound I claimed is indeed valid. So we can conclude number of maximal independent sets is at least larger of the two partite sets plus 1. Now, given just the order n, the larger of the two partite sets has at least n over 2 rounded up many vertices, so I can say this is at least n over 2 rounded up plus 1. Things do not change very much if I allow disconnected graphs. If I take arbitrary bipartite graphs, allowing also the graph to be disconnected, the change is really just by 1, because I can add one isolated vertex to the construction and it still works. So not a big change there from from connected bipartite graphs to arbitrary bipartite graphs. Okay, so we've had arbitrary twin-free graphs, number of maximal independent sets is at least logarithmic in the size. Bipartite twin-free graphs, number of maximal independent sets is at least linear in the size. We will look at one more class in a moment. I would just like to point out that we conjecture that what we proved here for bipartite graphs remains true for triangle-free graphs. This is a slightly stronger statement because any bipartite graph is automatically triangle-free, not necessarily the other way around. We think that the lower bound we proved for bipartite graphs is in fact true for arbitrary triangle-free graphs. But at the moment we do not have a proof of this. Here is a quick illustration showing that the extremal graphs are not unique. There are generally many possible graphs that attain the minimum number of maximal independent sets. Initially they're unique simply because there are not so many different graphs there, but the numbers grow quite quickly. So already with order 11 there are 73 different twin-free bipartite graphs that have the minimum number of maximal independent sets. If I extend to K3 free graphs, there are even 79. This is potentially one of the reasons that makes it harder to study the generalizations. There are many possible extremal cases to consider. Let's finally move to trees. So we've had arbitrary graphs, bipartite graphs, now trees. Here, actually the answer was already found earlier by Taletsky and Malishev in 2018. We provided an alternative and somewhat shorter proof for the same lower bound. So it turns out that for twin-free trees, the minimum number of maximal independent sets is in fact exponential in the size. So we've had logarithmic behavior, linear behavior, and now exponential behavior. So trees need to have at least an exponential number of maximal independent sets, provided they're twin-free. This is sharp. We see that the bounds grow roughly like 3 to the n over 5. The proof of this is basically an induction using a recursion for the number of maximal independent sets that was already used by Wolf, who studied the maximum. You can recursively determine the number of maximal independent sets in a tree if it has a decomposition like this into smaller subgraphs given by this formula here. So I take the number of maximal independent sets in each of these U's, take the product, then the number of maximal independent sets in each of these W's here, take the product, and that gives you the number of maximal independent sets in the whole tree that's shown here in a decomposed fashion. Again, there are actually many trees that attain the bound. The trees for which we get the minimum are not unique at all. There are several possible constructions. One of them is shown here. So the construction is basically by repeating this 5-vertex pattern a number of times and then adding something on the side. So the construction on the left here covers the cases where n is 0, 1, or 4 modulo 5. If we take 4 mod 5, then we don't need the blue and the red vertex. So then it's just these 4 plus number of copies of this. For 0 mod 5, we include the blue vertex. For 1 mod 5, we also include the red vertex. So that's the construction in these 3 cases that yields the minimum. The construction on the right is quite similar for 2 or 3 mod 5. 2 mod 5, we do not need the blue vertex. 3 mod 5, we include it. I can't really give you a particularly intuitive reason why the graphs need to look like this. To be entirely honest, it somewhat remains a mystery as to why the shape has to be precisely this. But so this particular feature here, this repeated pattern is quite important here. All right. The number of extremal trees grows. So for some values of n, the extremal tree with the smallest number of maximal independent sets is entirely unique. There are some where there are precisely 2 trees up to isomorphism, some where it's precisely 3 up to isomorphism. But in other cases, there are very many. Like when there are 18 vertices, there are already 60 possible trees that all reach the minimum number of maximal independent sets. So it's quite interesting that there is a bit of a discrepancy here. So residue class modulo 5 plays a role, among other things. As a corollary, in the previous cases, we also always looked at what happens if I allow the graphs to be disconnected. So the analog here for trees would be to allow forests, graphs whose connected components are trees. And again, the corollary is very similar to the previous cases. If I allow disconnected graphs, not very much changes from the connected scenario. I can include one more isolated vertex, but that's basically all. For every twin-free forest of order n, the number of maximal independent sets is at least the minimum number of maximal independent sets in a tree of n-1 vertices. So the best I can do is to take an optimal tree with n-1 vertices and add one isolated vertex to it that will not change the number of maximal independent sets, because that isolated vertex has to be a member of every possible maximal independent set. Let me conclude with some open questions, and then you will of course also have opportunity to maybe ask some questions if there are any. So I already mentioned the conjecture that we had, stating that the lower bound we got for twin-free bipartite graphs might extend to twin-free triangle-free graphs. Well, we do not know, but it seems plausible from at least our computer experiments that for triangle-free graphs and bipartite graphs, the minimum number of maximal independent sets, provided that my graphs are twin-free, is the same. What about other classes of graphs? We have done bipartite graphs. What about generally k-partite graphs? I do not know the answer. For bipartite graphs, the minimum number of maximal independent sets was linear, provided the graphs were twin-free. Does this remain true for k-partite graphs? Or do we have maybe faster growth? Slow growth. Instead of triangle-free graphs, you might want to consider graphs that exclude a larger clique, KK-free graphs. Or what about regular graphs? In all these cases, what can you say about the minimum number of maximal independent sets in these graph classes? Again, under the assumption that the graphs are twin-free. As I hope I managed to convince you, the simple condition of disallowing twins makes the question how many maximal independent sets a graph needs to have at least quite interesting, and we saw some rather diverse answers depending on which class of graphs we were looking at. So I think there is more room to investigate things here. And yeah, these are some of the open questions that come to mind, but there are certainly many other things that one might want to investigate around graphs, specifically the twin-free graphs and their maximal independent sets. Thank you very much, and I welcome any questions.
So, does anybody have any questions for Stephen Wagner? Yes.
Yeah, Professor, here, Karthik here. I have a few questions. Clique is a complementary notion of an independent set, right? So number of maximal clicks will be the same as number of maximal independent sets in the complement. Is it true?
Yeah, so you would immediately get results on the minimum number of maximal clicks in graphs. Now here we need a slightly different property. We would need that no two adjacent vertices have the same neighbors other than themselves, of course. So we have been considering graphs with the property that the open neighborhoods are all distinct. If we take complements, we would want to do the same, but with closed neighborhoods.
My question is a bit different. Thing is that we know that the independent set is a complementary notion of cliques. Is it possible to compute instead of, let us say that I want to compute the number of maximal independent sets in graph G. Is it true that I can go to the complement and compute the number of clicks in the complement? Maximal clicks in the complement?
Absolutely. Yes, absolutely. You can do this.
If that is the case, then this KK free graphs and all, there are works with respect to number of maximal clicks.
Yes, you can count them. My question is, what if you impose this additional property of being twin free, of course?
Oh, okay.
So in all these cases, what we've done here with arbitrary graphs, bipartite graphs, trees, imposed the condition of being twin free. What can you say about the minimum number of maximal independent sets? To the best of my knowledge, this is not known for any of these classes.
Oh, okay. Twin free condition also you want to take it to the complement?
Yes, but I would have to maybe switch it around. So, as I said, in a complement it would make more sense to forbid vertices having the same closed neighborhoods rather than open neighborhoods.
Okay, thank you.
Any other questions? I had one doubt in slide number 21. Maybe it's just maybe it's a coincidence or just see that when the number of vertices is even, it looks like the number of extremal bipartite graphs as well as the number of extremal K3 free graphs both are same for all even numbers. Is it a coincidence or maybe?
We conjectured that this is always the case.
It's always
so that they're the same extremal graphs for even n, but different for all n.
Okay, fine.
So yes, you're absolutely correct. We do not have a proof, but we agree that this is a sort of striking pattern.
Okay. Sir, maybe this is out of the thing, out of curiosity, I just want to know, probably is there any kind of motivation or an application for this study, theoretical motivation, or is there any practical applications for this?
We didn't consider any practical applications of this. There's a counting independent sets, different types of independent sets, does occur in different areas. For example, in the hard square model of statistical physics, it has been even studied in a theoretical chemistry context. But the motivation for what we did here specifically it was purely mathematical. So old questions dating back to as early as the 60s around maximal independent sets. I don't know what the original motivation was for, say, Moon and Moser and Muller. Erdős was involved in some of these questions as well. I don't know too much about the history.
Okay, fine. So, mathematical itself is enough to accept it as a problem. That's what I also feel. But anyway, I thought maybe now recently some applications has turned out. That was my curiosity. That's all.
I mean, these kinds of questions do come up in areas outside of mathematics. Whether having bounds on the minimum number of maximal independent sets has any immediate bearing is an entirely separate question, of course.
So if there are no further questions, we'll thank Professor Stephen Wagner for his very nice presentation. Probably even though it is an online talk, he made it so clear that we were able to understand. So we should thank him for that. Thank you, Professor.
Now, let's take a moment to express our sincere gratitude to Professor Stephen Wagner. We are truly fortunate to have his expertise available to us. I request Professor Stephen Wagner to accept our token of love, a small memento, which will be displayed on the screen.
Thank you so much.
Once again, I thank Professor Stephen Wagner and Dr. S. Francis Raj. Thank you, sir.
It's been a pleasure.
Now we will begin the contributed sessions. To ensure a more engaging experience, we have tried to organize the presentations across 3 venues based on topic areas. Venue 1, Father Joe II Seminar Hall, that is this hall. Venue 2, Chavra Seminar Hall, and Venue 3, IQAC Conference Hall. Presenters are kindly requested to proceed to their respective venues as per the schedule shared with you. Student volunteers will be available to guide you to the correct halls. As mentioned yesterday, we are also pleased to announce that Best Presentation Awards will be given for these sessions. Since the sessions are being conducted across 3 venues over 2 days, we will be recording the presentations for the purpose of fair and comprehensive evaluation. Please be assured that these recordings will be strictly confidential and will not be shared on any public platform. They will be used only by the judging panel.